Alright, and welcome back to another video of transport phenomena, where in this video we'll be solving this question on screen. And this question goes over a situation of an open air aqueduct on a decline. And the question at hand is, what is the height of this aqueduct given width and flow rate and the angle of declination? So we are also told that, hey, this is a root solving problem. Okay, so we're going to set up an equation to root solve. And we're going to start off with the starting point of Bernoulli's equation, which is equal to the negative frictional heating, which is 4F, F being the fanning friction factor, multiplied by delta X over diameter, V squared over 2. Okay, and we have the pressure term of the Bernoulli's equation, the velocity term of Bernoulli's equation, and the potential energy height change term of Bernoulli's equation. Okay, since it's open to the air, you know that there is no pressure difference and there is no change in velocity at all. And that tells us, what does that mean? That tells us is that the motive of the liquid motion, the motive is solely dependent on the change in height. Okay, the gravity is what motivates this liquid to move. So, well, you can go ahead and represent the change in height as using trigonometry as delta x. Okay, so we have the gravitational constant multiplied by delta x sine theta equals. Let's clean this up. We have negative 2 fanning friction factor delta x over d v squared. Okay, so what now? You notice that, hey, delta x cancels out, rather convenient. Now we have g delta x minus 2f velocity squared over d. No. Oh, we still have d. That's right. So, not quite good yet. You notice that we have some pesky terms that we cannot use to root solve. We have some unknown terms. We have diameter. Diameter doesn't make sense for this. We have a rectangular open channel, and we still have velocity. So the next thing that I would like to go off and do is let's take a control volume of a similar situation. I'm gonna turn off my phone here. Alright. It's getting blown up over there. Let's take this control volume of a liquid with a similar situation where the motive of the liquid is only gravity. So the force balance is, you have force of gravity, and then counteracting that is the force of the shear stress. Okay, the force of the shear stress is gonna look something like this. Ft. Let's do weighted perimeter. How do I want to do this? How about the we'll do this the long way. We'll do this the long way. I was trying to see if I can take a shortcut, but we'll do it the long way. The wetted area in which the liquid is in contact with the surface is going to be the outer area of the cylinder. And what is that? So Ft, we have shear stress multiplied by let's do pi d, so the circumference in terms of diameter, multiplied by h, the height of this control volume. We don't know what that height is, but we don't need to, as you can see in a bit. So rho g multiplied by the volume of the cylinder. The volume of the cylinder in terms of diameter is going to be pi d squared over 4 multiplied by h. So notice h cancels out, this cancels out, and pi cancels out. So what do we have? We have tau equals rho g over 4. Oh, rho g d over 4. So how do we relate these two expressions? Well, we have gravitational field constant. That never changes. Gravitational acceleration. So let's go ahead and find an expression to sub in for that. We have tau for shear stress over rho g. Okay, we can plug that in. We have 4 shear stress over rho g delta x. Oh, I'm missing a diameter. Oops. Where does that go? The diameter should go in the denominator. Negative 2f v squared over d. That's right, because I would like diameter to cancel out. That's what I like to see. So let's solve for, did I accidentally leave delta x in here? I did. Delta x should not be there. We canceled it out. So now what? Well, let's solve for, we need an expression for a shear stress, right? This is all in terms that we can solve for. So let's do shear stress equals negative fanning friction factor velocity squared. I duplicated g. G should not be there. Let's double check. G 4 tau rho d. 4 tau rho d. Okay. No more mistakes. We're all good here. Rho fanning friction factor velocity squared over 2 sine theta sine theta. We have all of our missing terms now. Just copying errors. Copying errors is what gets me. And we now have an expression for shear stress. Okay, in terms that we can find fanning friction factor. Fanning friction factor, we're going to use the Churchill equation, which is based on the Reynolds number, which we'll deal and wrestle with it in a bit. What's it called? Surface roughness, which we can assume is negative 10 to the negative 6, something like that. And we'll have density. We're not given density, but we can put it in a way that cancels out nicely. So the next thing is, let's perform a force balance on our channel. Okay, the channel again has the force of gravity counteracting the shear stress. Okay, the shear stress, and I'm just going to do algebra to get it all nice, is shear stress multiplied by the wetted perimeter over the area, the cross-sectional area. Okay, again, this is H, we want to know what the height of the fluid is, and W, the width of the fluid bed, which we were given, and multiplied by rho G. Okay, so let's take this one step at a time. Let's copy over our expression for shear stress, okay, or a rather nice expression. And let's tackle wetted perimeter over area. What is that? It's pretty easy. Wetted perimeter is twice that of the height plus the width, and the area is height times width. Okay? Equals rho G. Then we have our shear stress is negative rho F V squared over 2 sine theta, right? Notice that density cancels out, as I said earlier, and we are left with negative fanning friction factor V squared over twice that of sine theta multiplied by 2h plus W over h times W equals G. Okay, so G we know is a constant, so we can root solve for that, okay? And what do we, let's look at our left-hand side. What do we have? We have velocity, so let's take care of velocity really quick. You know that flow rate equals velocity times area, or no, right? That's right, velocity times area. So in other words, velocity is equal to flow rate, which we're given, over area. And area we can represent in terms of height and width of the channel, okay? So height times width, all taken care of. Now what about fanning friction factor? I mentioned earlier that we're going to use the Churchill equation in terms of and that takes in a Reynolds number and a surface roughness, and we're going to assume a surface roughness of 10 to the negative 6. So how about that Reynolds number? That Reynolds number equals rho VD over mu, So we are going to need some effective diameter, okay? And how are we going to find it? We're going to use this wetted perimeter over area idea. So the wetted perimeter over area, we have 2h plus w over h times w is equal to, let's do the wetted perimeter over area, cross-sectional area of a circle in terms of diameter. So let's do that really quick. Off to the side, the wetted perimeter is pi d over the area, which is pi d squared over 4. So cancel, 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 cancel. And reciprocal, we have 4 over d. In other words, d equals 4 times the quantity h times w over twice that of the height plus w. Okay, so we have a expression for diameter, which we can plug in here, which we can plug into the Churchill equation, which we'll reuse old code for that. So, in other words, hey, we have a expression that I can effectively root solve for. Okay, so I'll meet you right back in Python, and we'll code out a quick. This won't take long at all. It's a rather very simple root solving question, and we will get the answer. Okay. Okay. So now that we're in Python, I've reused some old code to give us the Churchill equation, which gives us the fanning friction factor in terms of the Reynolds number and surface roughness I've defined here, and I've defined the rest of our problem parameters. So let's get on. So how does root solving work? Well, it usually likes a function which has a vector of unknowns, right? We need a function to root solve, and that function takes in a vector of unknowns. In this case, we only have one dimension that we would like to find, so that dimension being h. H equals the first value in a vector. Okay. First thing we need to do is define a diameter, an effective diameter, which is 4 times h times w divided by the quantity twice that of h plus w. Okay. Now what? Now we have to take care of velocity. Oh, actually, let's do Reynolds number first. The Reynolds number, the Reynolds number equals rho times v times the effective diameter divided by v. Okay, and v is not defined, so we need to define v. Velocity is equal to the flow rate, which we're given, divided by h times width. Okay, I think all things that are accounted for here, and the fanning friction factor is equal to Churchill equation given Reynolds number and surface roughness, which I've defined above. Okay, so I think we're all good here. Remember that when you're returning something for a function which you would like to root solve, it ideally likes it in a list, okay, a Python list, and we have g minus, okay, meaning that it's going to make our expression match g. Right? G minus, what do we have? G minus f times v squared divided by 2 times sine theta. Okay, so this, actually I should probably keep this in a quantity, and then let's see, this whole, this whole quantity multiplied by 2 times h plus width divided by h times width. Okay, I think we should be good. So let's try it out. Let's do root function, and let's do 0.2 for the guess, and I needed to shift enter there, and fingers crossed, check that out, solution converge, and this is exactly what I expected to see. Okay, 0.14 meters is the height. Okay, so quick video here. pretty simple root solving question and solving a rather traditional chemical engineering problem here. Okay, so with that out of the way, I'll see you in the next video.